What is a full-stack engineer? Researchers found side channel attacks related to the design of CPUs that they were able to exploit all the way from JavaScript code running inside of a sandbox in a browser. That's about as full stack as it gets. There is no such thing as a full stack engineer. There hasn't been for a long while now. The entire stack has gotten so complex that it's unrealistic for a single human to truly understand all of it. But every bit of tangential knowledge that we acquire makes us better engineers. It makes us the people in an incident response channel that know what questions to ask. That's why, as long as I'm doing these, I'm going to push you to be curious and always learn a little bit more than you need. And this is why, in a lot of my content, I use the tool strace. We often have a program we can run, and that does something like read a file. But it does this by talking to the operating system, in our case, the Linux kernel. And these are in two separate worlds. The program can do maths and manipulate strings and parse JSON or whatever, all on its own in userland. But to do anything with the network or the file system, it has to talk to the kernel. Because the kernel has direct access to devices like network interfaces or disks, it runs in a different protection ring. Programs like Firefox run in ring 3, the kernel runs in ring 0, and if it's in a virtual machine, you have the ring -1 for the hypervisor that exposes virtual devices to multiple kernels, which allows sharing the physical devices underneath. Being in different rings means a program like Firefox cannot make a direct function call to the kernel. If it could, there would be no separation between programs at all, and they could do anything with the hardware. It would be chaos. What happens instead is that the kernel allows programs to run for a little bit and is able to stop them, switch to another program, run that for a little bit, switch to yet another program, and that is called preemptive multitasking. That's how you can run any number of programs concurrently, no matter how many cores you have. So at any point in time, the kernel knows everything about what's going on in each process. We'll pretend one program is one process is one thread to simplify. Each process has its own memory space, but it also has its own position in the code. It's in the middle of some function. That's the instruction pointer, also called program counter, and that's a register. Which is tricky, because registers are a shared resource. There's only one instruction pointer register per core, same as all the other registers. Each process can use racks, and RDX, and RDI, etc. to store whatever. Which means, when switching from process A to B, the kernel has to save the value of those registers somewhere and restore them before switching back to A. What I'm trying to say is, programs are guests on the computer. When a program needs to do something that only the kernel can do, it issues a system call, which is like a letter saying, I would like to read from this file descriptor up to this many bytes. Please write the result at this memory location. Sincerely, Firefox. This stops the program, transfers control to the kernel, which looks at the letter and either goes, not on my watch, buddy, and then you get an error back, or it goes, sure, I'll allow it, does the thing, and eventually transfers control back to the program. The short name for system calls is syscall, and we can trace them with a tool called strace, or if you're German, strace. Let's try it on cat, a command that prints the contents of a file to the standard output stream. We'll use a file that's on almost all Linux systems. Cat is indeed able to print that, and now let's run cat through strace, and we see a bunch of syscalls being made. Everything up until that point is just program initialization. Some of it is the dynamic linker, just loading the cat executable. Some of it is startup routines from glibc. The real work begins with that open add syscall, passing the path etc hosts along with some options. We can see it succeeds and returns file descriptor number 3. Numbers 0 through 2 are already taken by a standard input, standard output, and standard error. We then have newstatat, which cat uses to determine the size of the file it just opened, but which also returns permissions and timestamps, etc. fadvise64 lets the kernel know that cat is planning on reading the file sequentially, from start to finish, which might kick in some prefetching. Then cat uses the mmap syscall to allocate a buffer, the read syscall to read from the file into that buffer, the write syscall to write the buffer to the standard output, and so on until read returns 0, which signals that we've reached EOF, the end of the file. The munmap syscall is then used to free the buffer, the close syscall to close file descriptor number 3, and the rest is just cleanup. This is extremely useful. One thing we've learned from looking at this is that in this case, cat uses a buffer of 128 kibibytes. That's something we're able to tell just by looking at the communication between the process and the kernel without having to crack open the sources, which is a good thing because I looked at the sources for a few minutes and I don't really understand how it selects buffer sizes. That's the power of strace. Even if you don't have the sources or you don't understand the sources, you can tell what's actually going on. If you see a lot of small reads, it's a sign that increasing the buffer size will probably result in better performance. But of course, that begs the question, how does strace actually work? It is a user-land program, just like Firefox, just like cat, but it is able to spy on private communications between another process and the kernel somehow. So if we think in terms of security for a second, we either have a big exploitable hole here, or the kernel is allowing all that to happen. And the answer is yes to both. It's both of these. Linux has a security module named Yama after the final boss in Spelunky. It's the thing in charge of deciding whether a process can use the ptrace syscall to trace another process based on the relationship between them and the value of the ptrace scope setting. Ptrace scope equals 0 is kind of a free-for-all. Any process can trace any other process under the same UID, the same user ID. Ptrace scope equals 1 is restricted ptrace. You can only trace children processes, which sounds safer until you remember that a ptrace-based attack assumes they already have shell access as your user, so they don't need to snoop into a running browser to steal your cookies, they can just read them straight from disk. How does ptrace work in practice? We're not quite there yet, but I think we should start writing some Rust code that will eventually turn into a pretty bad version of strace. But first, a word from our sponsor. This video is sponsored by you. Thank you. I made a YouTube survey asking how y'all would feel if I were to do actual sponsored segments. And most of you were like, "We love you, baby, get that bread." And some of you were like, "I would rather give money to you personally." And I was like, you can already do that. I have Patreon, I have GitHub sponsors, I'm faster than Lime everywhere. It's not really hard to find me, it's linked in the description. While I have you, I'm releasing a new series of articles right now called Building a Rust Service with Nix. It is the Nix packages thing I've been talking about forever. By the time you watch this, the first article should already be out, and I'm going to unlock one article per week for 12 weeks, which is great because it's going to go through the month that I'm going to have to take off for health reasons. If you're a patron or a sponsor at $10 a month or above, you already have access to the whole thing, and you can generate friend links to share with your friends, or colleagues, or pets. I don't know why you would do that, they probably can't read it. Anyway, if you're not the waiting type, you can start supporting me for that reason, and then cancel later, because times are hard. I get it, it's fine. Whatever, back to the video. Bye. First, let's have our Rust program launch cat. There's a high-level command API in the standard library that we can just use. If we run that program, it runs cat. How does it do that? Because it involves creating another process and processes are managed by the kernel, it probably involves syscalls. To find out which, we can use strace. The important lines here are clone 3, then we have the output of cat, then wait for, which waits for cat to finish. However, I don't see the path bin cat anywhere in the output. That's strange. I suspect we're not getting the full picture. If clone 3 is cloning the process, that means we do get a new process with a new process ID, a new PID, and strace probably traces only the original process and not the clone. There's an option for that, --follow forks, or -f for short. Using it, we can see that after the clone 3 syscall, we have indeed two processes. Each line is preceded by the PID of the process it's for. In the child, we have a bunch of setup for signals, and finally, execve. And that is how it runs cat. It's a two-step dance. First we fork, which creates a child process as a clone of the parent. Unless you specify otherwise, the child has the same stack, but with copy on write semantics, so it can't actually mess with the parent, and execution continues from the same point in both. To actually have the child run another program, it has to do step 2 of the dance, invoking the execve syscall. This replaces its code and data in memory with an executable loaded from disk. Here, it's bin cat. And that liminal space between fork and exec is where a lot of cool and cursed stuff happens. If we print the PID of the current process at the start of main and within pre-exec, we can see that they're different. After fork or clone, they're basically the same, it's already truly the child process. And that's mighty convenient. It means before loading bin cat as the child process, we can give permission to the parent to trace us by doing a ptrace syscall with ptrace trace-meeee. Now this is not in the Rust standard library, but we can pull in the Nix crate to issue ptrace syscalls. And at this point, we're on our own. The program still runs fine by itself, but we can no longer run it under strace, not with -f at least. If we do, our trace-meeee call returns eperm, operation not permitted. That's because at that point, the child is already being traced by strace, and there can only be one tracer process. We can trace the parent still, so that we have a little chain of command. strace is tracing our program, which is tracing cat. And that turns out to be useful because we can see that the result of wait4 is not what it used to be. Before we called trace-meeee from the child, wait4's return value had with exited set with a status of 0, cat returned successfully. Now that we are calling trace-meeee, its return value has with stopped set with a stop signal of sigtrap. And that's not all. If we sleep for a few seconds after waiting on the child, it doesn't continue. We don't see the output of cat until after its parent exits, which presumably severs the tracer-tracee relationship, has the child reparented to PID1, in my case that's systemd, which allows it to run to completion. This is normal. This is how ptrace works. Once you've detached to a process, or it has asked you to trace it, it stops until you tell the kernel, that process may continue until it gets a signal, or until the next syscall it performs, or until the next instruction, which is what GDB uses when you do step I. Say we're only interested in syscalls. The first thing we want to do as parent is to wait until the child process does trace-meeee. We can't use wait for this, because that expects the child to exit fully. We have to use wait PID, which only waits for the child to change state. Let's try doing it once. Yeah, we get stopped. It tells us the child got sigtrap, that checks out. Now we need to tell the kernel the child is allowed to continue until the next syscall. Then we wait again and start all over again in the loop. And that works until eventually wait PID returns exited, and then we crash because, well, the child doesn't exist anymore. Knowing when syscalls happen is a good start, but knowing what they are would be better. Good news is that's the simplest part. Syscall is an x86-64 instruction. It needs to jump from ring 3 to ring 0, remember? So it has to be something the CPU knows about. Each syscall has a number that's put into racks, and various arguments go into other registers, which means if we read registers from the tracee, which is something ptrace lets us do, we can tell which syscall it's calling. Because racks is also used to return a value from the syscall, we'll print the value of orig racks, the original value of racks before the syscall. Look at all these. We've got 1, we've got 0, we've got 11. We've got no idea what any of those are. I don't know them by heart. We could look up those numbers one by one, or we could use a big JSON file that someone else has already built from the Linux kernel headers. The shape of the data is a bit awkward, but if we deserialize it to JSON value, we can pick out the fields we need to build a map from syscall number to syscall name, which is all we're going to need today. Then in every iteration of the loop, we just need to do a lookup and print the name, and look! We made our own strace. It's perfect. It's almost perfect. There's something that looks... Why is it printing everything twice? Very simple question, very simple answer. ptrace actually stops the tracee twice per syscall, first on syscall enter and then on syscall exit. If we want to track the return value of syscalls, we need to print only on exit. Simple enough, let's just ignore every other turn of the loop with a boolean we switch every time, and there you go. Now the obvious missing thing here is the arguments. The JSON file I use does have the argument types, but not their names. You can probably find a better source or just hard code everything. I'm really excited about this. If you've seen my video about the Rust program leaking memory, that was actually just heap fragmentation, you might be suspecting why. That's gonna have to wait for another video. Until then, take excellent care of yourselves, and I'll see you next time. Bye. When I was a kid, I learned the first 100 digits of pi, and also just some random strings. I would write random strings into a notepad and just learn them. At some point there was a bomb threat in the school that involved the computers, so they brought me in for questioning and found the notepad, and they thought I was code, but it wasn't. I was just learning random strings. I guess there were signs